Okay, we have discussed this theorem in a previous lecture, and now we want to give a proof of this theorem. So to remind you, we have two angles, alpha and beta, and we're basically trying to prove that the product of a rotation by alpha around some point A, followed by a rotation by beta about some point B, is a rotation by alpha plus beta about some point C. Unless alpha plus beta is an integer multiple of 2 pi, and then that product of rotations will be a translation. So we want to prove all of that. It's going to be basically rewriting these in terms of their matrices and taking the product of those two matrices and making sure that they can be rewritten in this form, whatever this matrix is. But one of the difficulties we have to deal with is that C is not known. So we have to somehow show there is a point C like this, whereas here, in fact, we will take A to be x1, y1, and B to be x2, y2. And then we want to show with those A and B and alpha and beta angles here that we can find a C, and we don't know what the C is, but we want to show we can find a C such that this works. This product is equal to this. So just writing down what the matrices are, we're going to get this. Now you might not remember the rotation matrices. I'm not expecting you to memorize them, but it's exactly what I have here for R alpha A. This is the rotation matrix that I gave you before, except for I had thetas here instead of alphas. And we did have the point x1, y1 before, so that's the same. For this rotation, we're going to have betas instead of alphas or thetas. And we have an x2, y2 instead of x1, y1. So this is the product we want to take. It doesn't look nice, and that's because it's not nice. First, let me convince you that we're going to have a cosine of alpha plus beta here, and minus sine of alpha plus beta, sine of alpha plus beta, and cosine of alpha plus beta there. So let's go ahead and make sure that we get at least this part. So the difficult part is going to be dealing with u and v. So let's check this part. So we begin by taking the first row and the first column to get the first row and column of this product. So I'm going to take the dot product of this with this. So I've started, I'm going to have cosine of alpha times cosine of beta minus sine alpha sine beta, and then plus 0. Okay, so we're just ending up with cosine beta cosine alpha minus sine beta sine alpha for the dot product of this and this. And it should be this, and we can see it is. This is the formula for the cosine of alpha plus beta. It's a cosine alpha cosine beta minus sine alpha sine beta. So this is in fact equal to that, which is the dot product of this and this. Okay, while we have this on the screen, let's look at the second row and second column and see if we also have cosine of alpha plus beta. So I want to take the second row here and the second column here and see if that product is also the same. In fact, we have a minus sine alpha sine beta and a cosine alpha cosine beta that we're adding together, as well as 0. So that does give us the same thing we had here, maybe in a different order, but we're going to have cosine alpha cosine beta minus sine alpha sine beta. And again, that will be cosine of alpha plus beta. So we do have the second row and second column giving us what we want, the second row and second column here, the cosine of alpha plus beta. Now let's look at the first row and second column. So looking at this and see what we have when we multiply. We're going to have cosine beta times the minus sine alpha and a minus sine beta times cosine alpha that we add together, as well as 0. So minus cosine beta sine alpha again, and then minus sine beta cosine alpha. Well, this is the identity of minus the sine of alpha plus beta. So sine of alpha plus beta is sine alpha cosine beta plus sine beta cosine alpha, and that's what we have here. Sine alpha cosine beta, and we have a sine beta cosine alpha here. But again, with the minus signs, we're going to get minus signs throughout, and that's what we want. We're ending up with minus sine alpha plus beta. And this one should be the same thing, except with a minus sign, so we should have plus signs here instead of minus signs, and that's the second row and first column. So we want to take the second row and first column. And sure enough, we're going to have a sine beta cosine alpha plus sine alpha cosine beta plus 0. So it's a little bit different order. We have sine alpha and cosine beta being multiplied together, as well as a cosine alpha and sine beta, or sine beta and cosine alpha being multiplied together. And you add those, and you're going to get sine of alpha plus beta, like we have here. So that justifies all of these. We can check the 0 as well. There's not much to check there. These will always be 0, 0, 1 when you're multiplying matrices like this. If I take the third row, so this row, and dot it with any of these columns, the first column, you're going to get 0, 0, 0. Take this row and dot it with the second column, you're going to get 0, 0, 0. And take this row and dot it with the third column, you're going to get 0, 0, and 1, adding together to give you the 1. So the matrix looks pretty much like we want it, because the R sub alpha plus beta, comma C, which we don't know C again, but the angle part should tell us that all of this is what we want. We still have to figure out what's going on with U and V, which is the messy part. So the messy part, again, this R sub alpha A, it should look like this with alpha replaced with alpha plus beta. We got that part okay, but we're not going to get this part easily, just replacing this with alpha plus beta. And we have to figure out the right point for that part. So let me look at what U is. So this is the first row and third column. So I'm starting the first row here and the third column here. I'm not going to do any simplification. I'm just going to take cosine of beta times this, and then I'm going to take the minus sine beta times this, and then 1 times this. Again, I'm not really going to simplify anything here. I'm just going ahead and write this down. So we have x1 times 1 minus cosine alpha times cosine beta. We have y1 sine alpha times cosine beta. And then this should be multiplied by minus sine beta, so we'll have a plus x1 sine alpha sine beta. Again, since it's minus sine beta, we'll have a minus y1 sine beta, 1 minus cosine alpha. And the last part is to multiply 1 by this, so I'm just rewriting that down here, x2 1 minus cosine beta plus y2 sine beta. So this is U. Again, I haven't simplified it, but that's what U is. For V, we want to get the second row and the third column. So we want to take the dot product of those two. So let's see what happens with that. So I have x1, 1 minus cosine alpha times the sine of beta. I have y1 sine alpha times the sine of beta. I have cosine beta times minus x1 sine alpha. I have cosine beta times y1 times 1 minus cosine of alpha. I have then just 1 times this, minus x2 sine beta, and a plus y2 1 minus cosine beta. So those are U and V. Now I'm going to simplify this a little by using the cosine of alpha plus beta and sine of alpha plus beta formulas that we talked about a little while ago. So let's see if this looks like the correct simplification here. So first, let me notice I have a plus x1 here and a minus x1 on this side. So those are just going to cancel each other out. I still have a minus x1 times cosine of beta here, so that's plus x1 cosine beta. And that's actually the first thing up here. So now I'm trying to make sure that the rest looks exactly like what's left here. So I have x1 cosine beta times 1, and again, I'll have a minus x1 times minus cosine beta that's giving me the same thing. So that 1 times this will cancel with the minus x1 times the minus cosine beta. And let me just eliminate things up here one at a time. I have x1 times cosine beta cosine alpha with a negative sign. That looks like part of the formula for cosine of alpha plus beta. Cosine of alpha plus beta is cosine alpha cosine beta minus sine alpha sine beta. That's over here times x1. Okay, so again, I have a minus cosine cosine beta and a plus sine alpha sine beta, so that will be a minus cosine alpha plus beta. So that corresponds to the x1 times minus cosine of alpha plus beta here. So again, let me clarify again, this is cosine alpha cosine beta. So that's x1 minus cosine alpha cosine beta, that's this part. And then you have a minus sine alpha sine beta with a minus sign here, so plus sine alpha sine beta times x1, which is this part. Next, we want y1. We have sine alpha cosine beta here, and we have a y1 with a sine beta cosine alpha here. Both those are plus signs because this has two negative signs here. So we have y1 with a sine beta cosine alpha and a sine alpha cosine beta. And that was the identity for sine of alpha plus beta. Sine of alpha plus beta, this here, is a sine alpha cosine beta plus sine beta cosine alpha. So those all will cancel. This I'm canceling will be the same thing as this plus this times this. Okay. The next thing left up here, we've gotten rid of every term in that first line. The next thing left up here is the minus 1 sine beta times the 1. Okay, so we do have a minus 1 sine beta right here. So those two are going to cancel. Notice I've now multiplied this by each of these, and those have canceled. So the next thing up here is x2 times 1 minus cosine of beta. And I have x2 times 1 minus cosine beta. So this and this will cancel, or in other words, I can get rid of that when I get rid of this. So this is taking care of x2 times this. So we're just left on the top with a y2 sine beta, but you can see the only thing left on the bottom is also a y2 sine beta. So those cancel, and we're done in terms of showing that u is equal to the second expression we have up here. V, you can do the exact same thing with, and that should equal this. So let's just start from the top here, x1 sine beta. I'm not going to cross these out, we're just going to do them quickly. We have an x1 sine beta here. We have an x1 times sine beta minus cosine alpha, and an x1 times with minus sign also sine alpha cosine beta. So that should be minus x1 sine of alpha plus beta. So that's this one. So that takes care of this as well as this. Then we have y1 sine alpha sine beta, and we're going to have a y1 cosine alpha cosine beta here with a minus sign. And so that's actually going to be minus cosine of alpha plus beta times y1. So again, this is cosine alpha cosine beta minus sine y1. And then minus sine alpha sine beta with an extra minus sign makes a plus sine alpha sine beta times y1. So we're done with the first line entirely here as well as this times this. And now we have a y1 times cosine beta here. We also have a y1 times cosine beta down here. This y1 we're not going to get rid of here, but it's a minus y1 here and a plus y1. So this y1 times this is done. We have plus y1 plus cosine beta here again, which is this times 1, and then the minus y1 and the plus y1. So the next thing up here is minus x2 sine beta. We have a minus x2 times sine beta. And the last thing is the y2 times 1 minus cosine beta. The y2 times 1 minus cosine beta is here. Now you'll have to check that I've actually crossed out everything and everything exactly once like I did in detail up here. But this is V after you simplify it. So this is what we showed the product of these two matrices are. It looked like this. And this U and V we've now simplified to these expressions down here. Now let's remind ourselves what we wanted this to look like. When alpha plus beta is an integer multiple of 2 pi times some integer, we need this actually to look like a translation. Well, I don't even need to know what u and v are. If I plug in alpha plus beta is 2 pi times an integer, cosine is 1, so both these are 1, and sine is 0. So we're going to get 1 for the cosine and 0 for the sine. And that will look like actually the translation matrix. The translation matrix that we had before looks exactly like this. You have 1, 0, wherever you're translating by for the x coordinate, 0, 1, whatever you're translating by for the y coordinate, and then you have 0, 0, 1. So this is how we had the form of our translation matrix. So without even knowing what u and v are, just by the first part of our work before, we can see that if alpha plus beta is an integer multiple of 2 pi, then the product of those two rotations is in fact a translation. But the hard part is when we have this rotation matrix, the product of these two, and we have alpha plus beta not being an integer multiple of 2 pi. So I've actually written this, so it's pretty nice. Let me remind you again what the rotation matrix is that we want. This is the rotation matrix we want. Here we want phi to be alpha plus beta, and we already have that as far as this goes. And we have the 0, 0, 1, but we need this also to be alpha plus beta here. And then this x1, y1, well, this was a rotation about x1, y1. We're trying to rotate about some other point that we don't know. x1, y1 were the coordinates of A, and x2, y2 were the coordinates of B. So we're not looking for x1, y1 here. Well, oddly enough, we do have what we want with x1 and y1 here and here. And what I mean by that is we have x1, 1 minus cosine of alpha plus beta, phi is alpha plus beta, plus y1 sine of alpha plus beta, again, phi alpha plus beta. So this is what we have right here with phi being alpha plus beta. And similarly down here, we have minus x1 times sine of alpha plus beta, plus y1 times 1 minus cosine of alpha plus beta. So this is the same thing as we have up here with the x1 and y1. But again, we're not really aiming for x1 and y1, and that's good because we have some other stuff here we have to deal with. So let me explain what I want to do next. What I want to show you next is that this part of u, the second part of u down here in the second line for u, is equal to x3 times 1 minus cosine of alpha plus beta plus y3 times the sine of alpha plus beta. So the same thing I have up in this line, but with x3 and y3 for some x3 and y3. And then that will mean that I can take the x1 plus x3, rewrite this as x1 plus x3 times 1 minus cosine of alpha plus beta plus y1 plus y3 times the sine of alpha plus beta. And I'll have what I have here with x1 and y1 being a different point, like I said. This will be x1 plus x3, and this will be y1 plus y3. So we'll have a different points, different things for x and y, times 1 minus cosine of alpha plus beta and sine of alpha plus beta. And I want down here to have the same x3 and y3. So down here, I want to rewrite this. So it looks like this, but with x3 and y3. So I want this to look like minus x3 sine of alpha plus beta plus y3 times 1 minus cosine of alpha plus beta. So I want to be the same thing as this, but with x3 and y3. So then when I combine these two lines, I'll have minus x1 plus x3 times sine of alpha plus beta plus y1 plus y3 times 1 minus cosine of alpha plus beta. So that will again enable me to rewrite this, replacing x1 and y1 in all these spots with x1 plus x3 and y1 plus y3, and the phis with alpha plus beta. So that's the goal at this point. If I can show I can do that with this line and this line, we'll be done. If I can replace this with something that looks like this, but x3 and y3, and this with something that looks like this, but with x3 and y3, then we'll be done. So again, the goal would be to show that this expression here, which is the same thing I have up here, the second line of u, is equal to the same thing I have in the first line of u, but with x3 and y3. And similarly, we want an equation. I'll get rid of this here. That bottom line is the same thing as the second line for v. And I want that equal to the same thing as the first line for v, but with x3 and y3 in place of x1 and y1. So that's the goal. And once I have that, again, I'll be done. So the real question is not what are x3 and y3 as much as do they exist? If I can show there are an x3 and y3 like this that satisfy both of these equations, we're done. This is just a system of two equations and two unknowns. So you solve it like you would any other system with two equations and two unknowns. Things are a little bit messy here, but what I'm going to do is simply eliminate the y3. So I'm going to multiply the first equation on both sides by 1 minus cosine of alpha plus beta, and the second equation on both sides by sine of alpha plus beta. So if I multiply this equation on both sides by 1 minus the cosine of alpha plus beta, I'll have a y3 here, a sine of alpha plus beta, and a 1 minus cosine of alpha plus beta. And if I multiply both sides of this equation by sine of alpha plus beta, I'll have a y3 times that sine of alpha plus beta times 1 minus cosine of alpha plus beta. So these two terms here, this one and this one, will look the same after that multiplication. And so when I subtract, the y3 terms will go away. So let's look at that. On the left-hand side, the y3 terms are going to go away when I do that subtraction. I'll also have this times 1 minus cosine of alpha plus beta. So I'll have 1 minus cosine of alpha plus beta squared. And I'll have this, when I multiply through by sine of alpha plus beta, I'll have minus x3 sine of alpha plus beta squared. And I'm subtracting, so it's actually going to become a plus. And what I'm going to have then is x3 times 1 minus cosine of alpha plus beta squared plus sine of alpha plus beta squared. So where is that coming from again? Just one more time. I've multiplied both sides of this equation by 1 minus cosine of alpha plus beta, and both sides of this equation by sine of alpha plus beta. And that gets rid of these two terms when I subtract, because they'll be the same, and I'll end up with x3 times 1 minus cosine of alpha plus beta squared. Then subtracting, I'll have a plus x3 times the sine of alpha plus beta squared. Now the right-hand side is going to look real messy. I don't really care about it. I don't have it. It doesn't matter to me what it is. I'm just going to put 3 dots there because it's completely irrelevant. Now we don't need to simplify this, but let's go ahead. I have a 1 here. When I square this, I'll have a cosine squared alpha plus beta plus the sine squared will give me another 1. And then I'll have the middle term when I square this, which will be minus 2 cosine of alpha plus beta. So again, the 2 is coming from this 1 squared and also cosine squared plus sine squared. And the middle term here is giving me the minus 2 cosine of alpha plus beta. Well, I want to divide by this, but is it 0? Well, notice the only way it can be 0 if the cosine of alpha plus beta is 1. Alpha plus beta would have to be a multiple of 2 pi, an integer multiple of 2 pi. But it's not. We're in the case where it's not an integer multiple of 2 pi. So since alpha plus beta is not an integer multiple of 2 pi, this is non-zero. And I can divide then by this to figure out what x3 is. So I don't care what this is. Once I divide by this, I know I have a value for x3. So I can find an x3 that we want, and I just need then to figure out what y3 is. So we get x3 equals something, but I can just go back to this equation. So I have an x3 value, bring this on the other side. 1 minus cosine of alpha plus beta, again, can't be 0 because alpha plus beta is not a multiple of 2 pi. So I can divide by this and I'd solve for y3. So I can get y3 and x3. The only thing that might make you feel a little uncomfortable is in the case that alpha plus beta is pi or 3 pi or some other odd multiple of pi, that's not an integer multiple of 2 pi, so it's not in the previous case we looked at. It's in this case. I have a 0 here times y3. And so it might bother you that I just said, well, you can take x3 and put it into the second equation. If you put it into the first equation and alpha plus beta is pi, you're not going to be able to solve for y3. Well, there are 2 ways to handle that. One is just to check to see that what we did works backwards, that once we have the x3 and we get y3 to make this equation true, then the way we derived this equation, you can work backwards and see this equation has to be true. The other way is just to look at alpha plus beta equal to an odd multiple pi separately. In that case, this is 0. This is cosine of that's going to be -1, cosine of pi, or cosine of 3 pi. This will be -1, so this will be 2x3, and this will be 0. So I can solve for x3 just by dividing by this expression. We'll get x3. And here, if alpha plus beta is pi, or 3 pi, an odd multiple of pi, this will be -1 again. So this will be 2y3. This will be 0. So we'll have 0 plus 2y3 equals something. And we just divide by 2 and we get what y3 is. So we can solve both of these equations in that case easily as well. So that gives us then x3 and y3. And so we see that we were able to solve for x3 and y3. And so that gives us then this theorem. We found C. In our proof, it was x1 plus x3, comma, y1 plus y3. But we weren't explicit about what x3 and y3 were. But we have a product of two rotations is a rotation about the C by the sum of the two angles here. And that happened when alpha plus beta was not an integer multiple of 2 pi. And we saw that when alpha plus beta was an integer